Right, now we're going to look at a different form of spectroscopy. This one involves basically blasting a sample with electromagnetic radiation and then measuring how much passes through the sample. So a small amount or a large amount will be absorbed by the sample that we're shooting it through, and then we can calculate how much is absorbed by measuring what comes through. In this method, it helps us identify compounds, look at their electronic structure, or just figure out the concentration of a sample. So there's two main types of spectroscopy that we're going to look at. Ultraviolet/visualization, which is UV-vis spectroscopy. And this would be one that we would use to look at the electronic energy levels, so be it atomic energy levels or atomic orbitals or molecular orbitals. Or we can use infrared spectroscopy, and this one's used more to figure out what type of bonds are present. So right here's a chart that shows the absorbance of light being emitted at different wavelengths. And so what we can see is, like right here, if we shoot a light with a frequency of, or sorry, a wavelength at 200 nanometers, then there's that much of it is absorbed. We do have on here two peaks, so two high points. What those would represent then is areas where it's actually absorbing a lot of the light. And so that one there is at about 480 nanometers. And so that means that if you shoot light through at 480 nanometers, it's going to absorb a lot of it. What that means is there's something then that is soaking up that energy, and so it's probably electrons. Because remember, when electrons are hit with energy from a photon, the electrons will hop up from one energy level to the next. Okay, and so that energy then is being soaked up by electrons. Whereas when it's lower energy, it's probably not enough energy to actually throw the electrons all the way up, and so they just stay where they are. So we've got a peak right there and a peak right there at 480 at 600. So that tells us a lot about the structure of an atom. And we can actually calculate the energy of those quantums by using our E equals HV equation. So down there we would use the wavelength to figure out the frequency. We'd use the frequency to figure out the energy that it's absorbing at. So here's a sampling of some of the transitions that are possible with a molecule between the 200 and 800 nanometers that we just looked at. So the different jumps that can occur, the pi up to the pi star anti-bonding, or the non-bondings up to either the pi star or the sigma star. Now keep in mind they're going up into those regions where there's instability, but then they fall back down and they release that energy again. So looking at those peaks actually tells us a little bit about the molecule or atom that we're looking at. So if it's making those transitions, we have one transition that goes from the pi bonding region, so that means the structure must have a pi bonding region. And it also has two possible peaks that would come from a non-bonding region. Remember, non-bonding electrons, those would be lone pairs. So in order for these particular peaks to occur, the element must have pi bonds, and it must have lone pairs. And so we think about oxygen and nitrogen, so double bonded oxygen, so O2 or N2, could possibly be one of those. So in order for these transitions to occur, the incident photon, or the photons that we are shooting at the sample, must have exactly the same difference in energy as those transitions. So an electron will not go up partway then fall back down. That's the whole quantum thing. They only exist in quantities. So in order for this transition to occur, we have to send in a photon with the same amount of energy as that transition right there. If it's a little bit less, nothing's going to happen. Same thing with that one and that one. So really there should be three peaks with this sample right here, if all three of these occurred. But the sample that we saw really only had two peaks, and so that means it would just have two of these possible transitions. And we could then go on to figure out which one it is by doing the E equals HV equation, and then figure out which one of these transitions contains both of those amounts of energy. So things that we view as colorless don't absorb anything within our visible spectrum of light. So they don't absorb any colors that we can see. But they still absorb energy. They just absorb UV light. So we can't see UV light. And so light between 200 and 400 nanometers, that's below our visible range. We can also run tests that would figure that out as well. And then colored species, so things that we see that have color, they will always absorb light from the visible spectrum, but they could also absorb light from the UV spectrum as well. All right, here's the Beer-Lambert Law. This one's actually becoming a lot more popular with the AP tests, so make sure you guys know this. It is on your equation sheet, and it's A equals ABC. How simple of an equation can you get? However, unfortunately, most of those letters don't actually stand for what they represent. So A stands for absorbance, but it has to be capital A. So the amount of light or energy that's absorbed is equal to the molar absorptivity, so this is a constant for a given sample. B is the path length of the sample, so the distance that light has to shine through, measured in centimeters. And then C is the concentration. All right, so here's a sample problem, and this one refers to a sample of hemoglobin, which is in your blood. It's what they use to carry oxygen. So a cuvette is like a finely polished test tube. And so what we've got here is a sample of this hemoglobin inside of a cuvette, and it says that the path length is 1 centimeter. So that means that the width of this test tube or cuvette is going to be 1 centimeter long. And we are shooting it with visible light, and then we're measuring how much goes through. So a small amount will come back through. This would be your initial intensity, this would be your transmitted intensity, and what we're measuring right here on this plot is the amount that's absorbed, so the difference between these two. And so when we shot through an incident light with 76 nanometers, we had an absorbance of 0.25, which means essentially that 25% of the light was absorbed by the sample. So we can use then this plot to figure out the molar absorptivity of the solution. That is the A, the small a, the constant. And then once we have that, we can find the concentration of the absorbance at 0.46 angstroms. 0.46 absorbance, sorry. And so to do that, we're going to use the Beer-Lambert law. So that is the capital A equals ABC. So in this case, we need to find out what the constant is for the sample, and so we're going to use some data that we already have. We know that the absorbance at 0.25, or when the absorbance is 0.25, it's equal to whatever A is, times B, which is our path length, that's 1 centimeter, times the concentration. And the concentration of that particular sample right there would have been the 1.61 times 10 to the negative fifth. And that's in molarity. What we're looking at there is just this point right here, essentially, on the graph. So when the absorbance is 0.25, the concentration is that right there. And then the second question is asking us, well, if it's 0.46, so if the absorbance is somewhere up here, what's the concentration going to be? First, we need to figure out what that A is. We can use it to get another equation. So we just rearrange this, solve for lowercase a, and we find out that it is 1.55 times 10 to the third. And the units on this would be essentially molarity over centimeters, or molarity centimeters on the bottom. Okay, now we can remember that number because it's a constant for this sample. So anytime we're talking about hemoglobin, the sample, the molar absorptivity is always going to be the same. So let's take that number then and use it to find the concentration if the absorbance is 0.46. So in this case, now we are looking for the concentration. So we can take that same A equals ABC equation, rearrange it so that C equals A divided by AB. So our concentration is going to be equal to 0.46 divided by the molar absorptivity, which we found was 1.55 times 10 to the third, molarity inverse times centimeters inverse, and we're going to multiply that by the path length, which is 1 centimeter still. Now, if you're following along with your stoichiometry at home, you're going to see that centimeters cancels out centimeters. We're left with molarity, which is good because we're finding concentration, and so it should be molarity. And when we solve this out, we find out that C is equal to 3.0 times 10 to the negative 14th, and that would be molarity. So what this means then is if we put a sample in there of an unknown concentration into our UV-Vis spectroscopy device, we could calculate what its concentration was based upon its absorbance. All right, now let's talk about IR spectroscopy. So what this does is it actually tells us about the bonds that are occurring. So all covalent bonds in molecules, they actually vibrate back and forth. And so what's happening is it's not just a straight stick line like we would normally draw. Think of it more like a spring where it's bouncing back and forth and back and forth. And they're kind of finding that interaction potential. And then we talked about how it has less potential and it can kind of go up and down on either of those. And so it's just bouncing back and forth like that. Now it vibrates essentially with a frequency. Okay, frequency is how often something occurs. And so if we shoot it with IR radiation, we can cause it to vibrate even more because we hit it with exactly the frequency that it needs in order to vibrate. And different bonds have different kind of sweet spots of radiation or of IR that are going to cause them to vibrate more and more. And so by bombarding a particular sample with IR radiation, we can then measure what different bonds are in there based upon what different levels of IR radiation or what different frequencies cause it to vibrate more or less. So here's just a table that shows us some examples. So if we had a peak for wavelengths that was between 3.38 and 3.51, it's probably a C to H bond. If we have one between this range, it's probably a double bonded C with an H. You know, if it was a amine, so a nitrogen to hydrogen, it would be within this range. And we could do the same thing with the wave numbers. So this would be the centimeters inverse. And this one would be the micrometers. And a wave number is just the inverse of the wavelength in centimeters. So in organic chemistry, molecules are named based upon functional groups, and so we can use this to identify what type of molecule something is. So like all alcohols contain hydroxides or OHs, carboxylic acids contain the COOH bond, and we can identify those through IR spectroscopy. So we can have an unknown sample and figure out what type of compound it is based upon the types of bonds it's got. All right, here's a chart showing a particular sample that was put through an IR spectra. And we see a couple different peaks on here. And there's one big one in particular right there. And so that particular peak actually aligns with the C double bonded to O peak. And so that actually matches up with this sample right here. So this is the IR spectra for this guy. And we can see that this peak indicates that little bond right there. So this is called characterization. After you do a reaction, let's say you're trying to make this molecule right here. So you've got your sample of it, you need to test it for purity. And so what you would do is you would take it to an IR spectra, you would run it through, and you would make sure that it matches up with your structure. So if you got your sample back from IR and that wasn't this peak right there, probably means you messed something up or that there's a large impurity in your sample.